Over the last few lectures, we have covered quite a lot of group theory, a decent amount of abstract group theory, and some group representation theory. At long last, we are in a position where we can fulfill, at least in part, the pledge that we made at the very beginning of the course. After all, we were studying this group theory not for the sake of the mathematics, which is fascinating, but primarily because we want to use this in a physical application. So today I am going to talk about the first such physical application of finite group theory. And this is in the theory of molecular vibrations. Now, this is not to say that we have completed our entire study of abstract group theory or even abstract group representation theory, for the simple reason that there were many topics which we simply didn't touch, and some of those topics we will need in specific applications later, but we have covered most of the basics. So if we need anything more, we are going to talk about them when we need them. Of course, we also must remember that a huge part of group theory, which is the theory of continuous groups, Lie groups in particular, have not been touched upon yet. That will be most of the rest of our course. However, let me just talk about a few physical applications where our knowledge of finite group theory will be enough to draw important physical conclusions. And the first such topic is that of molecular vibrations, something which we are going to talk about today. This particular topic, molecular vibrations, is a subtopic of a more general class of subjects which come under small oscillations. This is something which you must have studied in some detail in your classical mechanics class. We are going to do a quick recap of the necessary theory before we go on to apply group theory to this particular problem. Now, in order to apply group theory, which is after all a theory of symmetry as far as most of physical applications are concerned, we need to consider a molecule which has a lot of symmetries. And what we are going to do is we are going to assume that there is a fictitious molecule called triangulene, which is shaped like an equilateral triangle, at least when it is in equilibrium, and it is composed of three identical atoms at three corners of an equilateral triangle. Come to think about it, this is not so fictitious. After all, the ozone molecule is an example of this kind. Now, primarily for simplicity, I am also going to make the assumption that the atoms can only move in two dimensions. So, while the picture that you see now, drawn in red, is the equilibrium configuration of the molecule, when the atoms move away from their equilibrium positions, the triangle would no longer be equilateral perhaps, it would just stretch into some other triangular configuration. Now, this assumption that we have made that the atoms can only move in a plane does simplify our analysis a bit, and it may seem like an unphysical thing to demand for a real molecule, where of course the atoms can move in all three dimensions. As it turns out, the additional freedom which the atoms would have if they were allowed to move in three dimensions does not really add much of non-trivial physics to the problem. In fact, the essence of the physical problem is perfectly captured by even this two-dimensional version. We will see why later. Now, what we are interested in is the situation where the atoms suffer small displacements from their equilibrium position. So, the instantaneous positions of the atoms, which I have drawn in blue, differ from their equilibrium positions, the ones in red, by some displacement vectors. And we are going to consider a situation where the displacements are small at least compared to basically the scale of the molecule. And actually, here, the reason why we are considering small displacements, as you all know, is that we are going to treat the potential energy of the system in terms of Taylor expansion and keep the lowest non-trivial terms, which happens to be the quadratic terms. So we will need to describe the system using some coordinates, and what we can always do is stick Cartesian coordinates basically horizontal and vertical ones in this picture, to each one of the equilibrium positions of the atoms and measure the displacement of individual atoms using coordinates x1, x2, x3, x4, x5, x6 for the first, second and third atom respectively, in terms of basis vectors which are indicated in the picture. Now, this particular choice of basis happens to be a very simple one to come up with, and I'm pretty sure this is the one which most of you will start with. It turns out that this is not a very good choice of basis for this particular problem. What do I mean when I say this is not a very good choice? I mean that the problem does not present itself in a very simple way if you use this particular basis. However, the basis which you could use, which would actually help you solve the problem very, very simply, is not at all an obvious basis. And in fact, one of the major applications of group theory to this particular problem would be to tell you how to choose a basis in which this problem essentially becomes a lot simpler. But that will come as we go along. For the time being, let's just keep in mind that in this particular case, we have chosen a set of vectors E1, E2, E3, E4, E5, E6. E1 and E2 are tied to the first atom, E3 and E4 to the second atom, E5 and E6 to the third atom. And these 6 basis vectors form a linearly independent spanning set or a basis for the underlying vector space. Now, in order to study the dynamics of the problem, we need to be able to write down its Lagrangian. And as you all know, there are 2 components to the Lagrangian: the kinetic energy, which here is pretty simple. All you do is take the individual kinetic energy contributions due to each and every one of the coordinates, half mi xi dot square, and add them all together. Now here, because we are using 3 identical atoms, all the 6 m's that we use in the sum, m1, m2, m3, m4, m5, m6, are all equal and equal to m. In any case, m1, m2 essentially refers to the same particle. So m1 and m2 will always be equal, m3 and m4 will always be equal, m5 and m6 will always be equal. The fact that all 6 are equal to each other is simply because we are using 3 identical atoms. If we talk of a molecule with a slightly lower degree of symmetry, for example, a molecule of type AB2, where you have 1 atom A and 2 B atoms, then of course M1, M2 would be equal, but M3, M4, M5, M6 would be equal to some other value. In fact, the reduction in symmetry because of the substitution of one atom in an ozone molecule by a different atom, maybe even an isotope, can lead to rather interesting consequences, and group theory is a wonderful tool for studying that. But that is for later. For the time being, let us take a look at this situation where all 3 atoms are identical. The potential energy is the next ingredient. Of course, it will depend on each one of these coordinates x1, x2, x3, x4, x5 and x6. We are going to assume that the zero of the potential energy has been chosen to be the equilibrium configuration of the molecule, which is the configuration where x1 through x6 are all 0. That is, all the atoms are sitting in their respective equilibrium positions. Now, if I make a small displacement approximation, we can expand out this potential in a Taylor series, and as you all know, the standard theory will tell you that the first derivative term, the term linear in the xi's, will vanish because xi equal to 0 stands for equilibrium. So the smallest non-trivial term that you are going to get is a quadratic one, sum over both I and j running from 1 to 6 of half del 2v del xi del xj xi xj. Now, it will be much simpler if we changed our coordinates to mass weighted coordinates, where we absorb the square root of the mass inside the coordinate itself. So qi is root mi xi. The advantage that this gives us is that now the kinetic energy term simplifies a lot, because qi dot square is simply mi xi dot square. So the kinetic energy term simply becomes half of sigma qi dot square. That's the first term in the Lagrangian written here. The other term, minus half sum over both I and j, running from 1 to 6, Fij qi qj, is simply the potential energy term where Fij are just these mixed partial derivatives, del 2v, del qi, del qj. Of course, the upper limit of 6 that we have used here in both the sums is because we are using a system with 6 degrees of freedom, that is 3 atoms which can move in 2 dimensions. The generalization to an arbitrary molecule with n atoms moving in, say, perhaps 3 dimensions should be sort of obvious from here. Now, it is a rather simple task to find out the Euler-Lagrange equations of motion corresponding to that particular Lagrangian, and it turns out that we get a bunch of coupled differential equations. The second derivative of qi turns out to be minus sum over j running from 1 to 6, Fij qj. Once again, the upper limit of 6 is for this particular system. In general, it would be j equal to 1 to n. But what is important here is that the acceleration of the ith generalized coordinate or mass weighted coordinate depends not only on the value of this particular coordinate, it depends on the value of all the coordinates, at least as long as the Fij's are non-zero. It may turn out the sum of the Fij's are 0, so the displacement of a particular coordinate may not affect some other coordinate, but in general, the value of every coordinate affects the acceleration of every other coordinate. That is, we have a set of coupled oscillators. Now, this is really a simple harmonic system in disguise, simply because all the forces, that is, the entire right hand side, is linear in displacements. And we know how to handle this. That is a topic that you have definitely studied in classical mechanics. But let me just go through the standard steps quickly. This will serve both as a reminder if you have forgotten, but more importantly, it will serve as a way of fixing our notation. So what we do first is, instead of writing this particular set of equations component by component, one equation for each coordinate, we can write them as a single equation by rolling up the coordinates q1, q2, q6 in a single vector called q and writing down a matrix curly f whose ijth element is this small Fij. And if I do that, the equation simply becomes q vector double dot is minus the matrix f acting on the column vector q. This is just for notational convenience. We could, of course, keep on using the component by component version throughout, and that would not have changed the final conclusions. But this actually helps us to simplify some of the writing. For example, what we can always do now is try to change our coordinates from small q vector to some capital Q vector. So a bunch of new coordinates, capital Q1, capital Q2 up to capital Q6 or capital Qn in general. And the way these two are connected to each other is by a linear transformation or some matrix S, which has to be an invertible matrix for this transformation to be a valid coordinate transformation. If I take this value for small q vector and plug it back in my differential equation, capital S being a constant matrix comes out of the derivative and you are left with capital S, capital Q vector double dot equals minus curly f times capital S q vector. All we have done here is replaced small q vector by capital S times capital Q vector, and this is the equation we'll end up with. Of course, since capital S is invertible, I can now rewrite this equation entirely in terms of the second derivative of capital Q. Q double dot is minus S inverse curly f S q vector. So, under a coordinate transformation, the force matrix curly f undergoes a similarity transformation. And you must have guessed what's coming next. what we can always do is choose a particular similarity transformation which diagonalizes this curly F and gives you a diagonal matrix curly D. You may worry about whether curly F is diagonalizable at all or not, but notice that curly F essentially has components, ij components given by del to capital V, del qi, del qj. And that means curly F's ijth component is equal to curly F's jith component. Hence, curly F is a symmetric matrix, and symmetric matrices are diagonalizable. Not only are they diagonalizable, it's a very standard result in linear algebra that they are orthogonally diagonalizable. So what we can always do is choose this matrix S to be an orthogonal matrix. In other words, S inverse and S transpose could be one and the same. And with this particular choice, what we have is a set of equations which were coupled equations in terms of the original small q have become uncoupled. And now you have capital Q vector double dot is equal to minus some diagonal matrix acting on capital Q vector. And if I just write down the components of the diagonal matrix, the diagonal elements, as omega 1 square, omega 2 square and so on, I will immediately see that these equations become qi double dot plus omega I square qi equals 0. Now, some of you may have wondered why I said that the diagonal elements must be omega 1 square, omega 2 square and so on. Why do I know that they are positive? And the answer lies in the fact that capital V has a minimum at the equilibrium position, which means that whenever you move away from the equilibrium, it can only go up. And the only way you can ensure that is to demand that this curly F matrix has eigenvalues which are all positive. And these eigenvalues, of course, are the diagonal elements we are talking about. At this stage, we have reduced the problem, which used to be that of a set of coupled differential equations, into a bunch of uncoupled differential equations. And each of these equations are, of course, very easy to solve because they are just simple harmonic oscillator equations. Thus, each of these normal coordinates capital Qi, which are some linear combinations of the small qi's, execute simple harmonic oscillations as a function of time, and so the problem has essentially been solved. These omega i's are nothing but what are called normal mode frequencies of this particular system, and the coordinates capital Qi give you the normal modes, the precise combinations of the small qi's which oscillate together into a single simple harmonic oscillation. So capital Qi and omega I are the normal coordinates and normal frequencies for this particular problem. So in a sense, our problem is really very simple. All we have to do is start with this force matrix curly F, which is a symmetric matrix, and diagonalize it. So the prescription is clear. Why then do we need to use a technique like group theory here? And the answer lies in the fact that determination of the normal mode, even for such a simple molecule as triangulene, requires a diagonalization of a 6 by 6 matrix. This is no mean task if you were to do it by hand. And of course, for a bigger molecule, the size of this matrix goes up and the difficulty grows a lot. Now, in this particular case, 3 of the normal modes are already known. 3 of the modes where the value of omega I is something we already know for sure. These are 2 translational modes, that is, modes in which the molecule can shift along the plane in any direction, but there are 2 independent directions it can move in. So 2 translational modes and 1 rotational mode where the molecule can turn as a whole while sticking to the plane, that is, rotate about the z-axis, the axis perpendicular to the plane. And these are modes which correspond to zero frequency motions. What does that mean? It simply means that when a molecule translates as a whole, there is no restoring force which acts on the atoms. So there is no tendency for the atoms to come back to their equilibrium positions. Hence, no oscillations. The same goes for the situation where a molecule rotates. When a molecule rotates, the relative positions of the atoms do not change except in orientation, and as a result, there is no restoring torque, and the thing simply keeps on rotating forever without any tendency to come back to the equilibrium position. So these are so-called zero frequency motions. This leaves three other motions which are what we call vibrational motions or internal motions of the molecule, and these are the ones we are really interested in. In a general n-atom molecule in 3 dimensions, we will need to diagonalize a 3n by 3n matrix, and this could be very huge depending on the value of n, and there are 6 zero frequency modes in such cases, because now that we are in 3 dimensions, the molecule can translate in any of the 3 independent directions and can rotate about 3 independent axes. So if you leave out these 6 translational and rotational degrees of freedom, this leaves us with 3n minus 6 vibrational frequencies. And to determine these, what we need to do is to diagonalize a 3n by 3n matrix. Now, when n is large, diagonalizing a 3n by 3n matrix is no mean task at all. If you remember your basic linear algebra, in the process of diagonalization, the first thing you usually do is find out the eigenvalues. And for that, you have to essentially solve a 3n degree polynomial equation, the characteristic equation for this particular matrix. Now, that is usually very difficult to solve, and beyond degree 4, we don't have any explicit formula available for the general case. But we can always solve for these eigenvalues, maybe by using numerical techniques or whatever other tools you have at hand. But be that as it may, diagonalizing a huge matrix takes a lot of effort. So the standard procedure, of course, is you find the eigenvalues first and then use the eigenvalues, plug them back into the basic equation and use them to find out the eigenvectors. On the other hand, if you somehow knew the eigenvectors from the very beginning, then finding out the lambda in Ax equal to lambda x would be absolutely trivial. All you would have to do is apply the matrix A on your eigenvector x. Whatever you will get has to be a multiple of x, and once it is, the factor by which you are multiplying x to get the result is very easy to find out. So, if you knew the eigenvectors, finding out the eigenvalues would be trivial, but usually what we have to do is find the eigenvalues, from that find out the eigenvectors and put the eigenvectors together into a square matrix in order to get the diagonalizing matrix. The important thing here is symmetry can help us in identifying these eigenvectors for the system. So rather magically, the problem gets turned around into something much simpler. You just find out the eigenvectors using symmetry, that is, using group theory. And now that you know the eigenvectors, you can simply apply the matrix on it to find out the eigenvalues. Now, there is a catch there. I have said at least in part. We will see why in part. But you will still see that even in a situation where symmetry is not enough to completely identify the eigenvectors, it helps us to cut down the size of the problem by a huge amount. Now, one reason why symmetry cannot help us to completely identify the eigenvectors is that sometimes these vibrational eigenvectors can be mixed up with translational eigenvectors as well. That is, instead of getting a vibrational normal mode, what you may get is a combination of a vibrational normal mode and a translation. Now, in order to ensure that you get a purely vibrational mode, what you can do is insist on this particular additional constraint equation. Sigma mi ri, which is of course just total mass times the center of mass coordinate, that must stay fixed, and let's say fixed at 0. That is, the molecule does not translate as a whole. This condition will help us eliminate some of the combinations where symmetry considerations cannot help us to separate the translational part from the vibrational part. You will see applications of this later on in this lecture. Now, in order to understand how symmetry actually helps us in determining these eigenvectors, let us go back to the original equations. The equations, as you remember, were a bunch of coupled differential equations which we rolled up into this matrix equation q vector double dot equals minus curly f times q. Now let us consider any coordinate transformation where q goes over to q prime, that is mq. We have already seen a special case of a coordinate transformation earlier where at the end of the day the curly f matrix changed into a similar matrix which is diagonal. But here we are considering some other coordinate transformation. Now since q prime is mq, q of course is m inverse q prime, and if we plug that back in our equation, we have, in a very similar fashion to our determination of the normal modes, this new equation m inverse q prime double dot equal to minus curly f m inverse q prime. There's a typo there, it should be q prime on both sides. And this will help us to rewrite our equation into an equation for q prime. Q prime double dot is minus curly f primed q prime vector, where curly f prime, the new force constant matrix for this new set of coordinates, is simply given by m curly f m inverse. Once again, a similar transformation has been done on curly f to get a new force constant matrix. This is exactly what we did when we talked about normal coordinates. There the aim was to find out a similarity transformation which will diagonalize the curly f, and that is what gave rise to curly d in place of curly f prime. But now we are considering a different situation. Suppose this particular coordinate transformation that we are talking about happens to be a symmetry of the system. What that means is, if I carry it out on the system, while you keep your back turned to me, if you turn back, you will not be able to tell whether I have made that change or not. And this means curly f prime, the new force constant, has to be the same as curly f, the old force constant matrix. If that had changed, then the physical configuration would have been different before and after the symmetry, which of course can't happen because that's exactly what a symmetry means. So as a result, what we conclude is any matrix which represents a symmetry action must obey m curly f m inverse is equal to curly f, that is, curly f must commute with all the representation matrices of the symmetry group of the system. Now, one situation would have been wonderfully simple. If the action of the symmetry group on the set of molecular vibrations were to furnish an irreducible representation of the symmetry group, the problem would simply become trivial, because then curly f would commute with each and every one of the representation matrices in an irreducible representation, and then Schur's second lemma would have told us that curly f would have to be a multiple of the identity, which means it's a scalar matrix and the eigenvalue would be simple. Just apply curly f on any vector whatsoever, you will end up with a multiple of that vector times the number, and that number is your eigenvalue. Now, usually we will never be this lucky. The representation that we will come up with on the space of molecular vibrations would usually be reducible. So Schur's second lemma will not really help us out there. But we already know something that will. This is a situation which is tailor-made for the Wigner-Eckart theorem. We had made a special version of this theorem in an earlier lecture where we talked about an operator which commuted with each and every one of the operators in a representation for a particular symmetry group. That is exactly what we are talking about here. Curly f is a matrix which commutes with each and every matrix which represents the elements of a symmetry group. And we will use the Wigner-Eckart theorem to draw conclusions about the eigenvectors of the system, and this is how we are going to actually land up simplifying our calculations a lot. But first, we need to thoroughly understand the representation of the symmetry group of the system that is furnished by molecular vibrations. The symmetry group is, of course, our old friend, the symmetry group of the equilateral triangle. We have been calling this group S3 simply because it is isomorphic to the group of permutations of three objects. Now, we have already seen several representations of this particular group, but this particular one that we are looking at right now is slightly different from the ones we have seen before. On the other hand, it is also pretty well related to some of the ones we have seen before. For example, if you carry out a particular symmetry operation, let's say a reflection, then what happens to the molecular displacement vector is that the displacement of a particular atom gets reflected along that particular line. However, it may so happen that the atom itself shifts position from one point to another. So here, the representation, which is after all a reflection of the group action, comes in two pieces. One, which atom goes where, and two, what happens to the atomic displacement vectors under the action of this particular group element. So it is not a surprise that we can actually write down the representation that we are talking about here as a direct product representation, which essentially captures these two actions one after the other. Let us take a look at the simpler one of the two, the question of which atom goes where. So, to begin with, let us start with the trivial operation which every group has, the identity operation. What we have done is we have labeled the three atomic vertices A, B and C, and of course under the identity operation, A, B and C stay unchanged. So A maps to A, B maps to B and C maps to C. We can convert this particular statement into a matrix representation by imagining that there is a vector space in which A, B and C, the three vertices, provide you with the three basis vectors. So we are talking of a three-dimensional vector space. It is a rather unusual kind of vector space in the sense that we will be talking about things like adding alpha times A plus 2 beta times B. And while that make perfect sense in terms of the position vectors in two dimension, but that of course will not give us A, B and C as three independent vectors. Here we are thinking of in terms of some abstract space which essentially has A, B and C as three basis elements. Frankly, we don't really need to go very deeply into the nature of the vector space simply because the action of the group elements on the basis vectors, in this case on the vertices, is all that is really important for us right now. Of course, given this particular action of the identity, the corresponding matrix representation will be the obvious one. In fact, the obvious one which stands in for the identity in any linear representation, the identity matrix of the appropriate order. In this case, a 3 by 3 identity matrix. Things get a bit more interesting when we look at the other group elements. The next group element that we are going to look at is the reflection A, which is a reflection through a median of the equilateral triangle passing through the vertex A. Now, under that, A of course stays put, but B switches to C and C switches to B. So this is what the map A does to the vertices. And we can easily write down the matrix representation for this. A goes to A, of course that means it has 1, 0 and 0 as coefficients that will form the first column of our matrix. B goes to C, 0, 0, 1, that's the second column. And C goes to B, 0, 1, 0. That's our third column. So this is the corresponding matrix. Well, the other group operations can be easily tackled along the same lines. Small b, which is the reflection in the median passing through capital B, the vertex, of course keeps capital B unchanged and switches A and C. And this gives rise to this particular matrix as its matrix representation. Small c, again pretty straightforward. Capital C stays unchanged. A and B switch. So you get 0, 1, 0, 1, 0, 0 and 0, 0, 1 for the corresponding matrix. Under the action of D, all three vertices switch positions. A goes to B, B goes to C and C goes to A. And this means that the corresponding matrix is going to be 0, 1, 0, 0, 0, 1, that's B going to C, and then C going to A, that's 1, 0, 0 for the third column. Finally, we come to the last element of our symmetric group, the 240-degree rotation, F, and under that A goes to C, B goes to A and C goes to B. So, the corresponding matrix simply is 0, 0, 1, 1, 0, 0, 0, 1, 0. You can easily check that these 6 matrices respect the group multiplication law. If G1 and G2 is G3, then the matrix corresponding to G1 times the matrix corresponding to G2 is the matrix corresponding to G3. That is, these 6 matrices furnish a 3-dimensional matrix representation of the group S3. We have already seen other 3-dimensional representations of this particular group, but we have not really seen this one. But this, of course, is a very, very simple representation. Now, as we said already, our representation, the one we are interested in, is one which takes into account 2 things. Where do the vertices go? That is, which atom goes where under a group operation, and what happens to the atomic displacement vectors under this operation. Now, what happens to the atomic displacement vector is easy to describe by just writing down the atomic displacement as a vector in 2 dimensions, and we have already seen this before. The representation we are going to talk about now is a representation furnished by the action of the group on vectors in a 2-dimensional plane. Just for the sake of completeness, let me quickly go through that particular representation. You describe the representation by saying what happens to the basis elements under the action of the group elements and converting that, of course, to matrices. So, under the action of E, E1 stays E1, E2 stays E2. That's, of course, what happens under the identities action every time. And this is a 2-dimensional representation. The corresponding matrix, of course, will be a 2-dimensional identity matrix. Things get a little more interesting when you look at the first non-trivial operation in the symmetry group, which is the reflection small a. A reflection through a median, which is a vertical line here. That is, the reflection line here coincides with the direction of E2. Hence, E2 stays the same under the reflection, and E1, being perpendicular to it, flips over and changes sign. The corresponding matrix version is easily found to be -1, 0, 0, 1. Slightly more non-trivial than this is the action of small b, a reflection through another median which makes an angle of 30 degrees with the vector E1. So, when you reflect E1 in that, it flips over and turns through a total of 60 degrees and essentially becomes a combination of E1 and E2. This particular combination is cosine 60 degrees E1 plus sine 60 degrees E2. As you must have realized, I am using C and S, these 2 letters, to stand for cosine 60 degrees and sine 60 degrees, half and root 3 by 2 respectively. This is just to declutter the screen and cut down a bit on the number of different numbers that you see on the screen at a given point of time. It's easy to see that E2 becomes the vector E2 prime shown on your screen, and that this particular vector is sine 60 degrees E1 minus cosine 60 degrees E2. Corresponding matrix is straightforward. You take the coefficients C and S of E1 prime in terms of E1 and E2, write them down as the first column of your matrix. S and minus C form the second column. Of course, in this case, since the matrix happens to be symmetric for this particular group element, it doesn't really matter whether you went column by column or row by row. But the rule is, of course, the first basis vector gives you the first column, the second basis vector gives you the second column, and not the row. The other reflection, C, is also easy enough to figure out. It's very simple to see geometrically that the vector E1 prime will make an angle of 60 degrees with E1, but in the downward direction now. So basically it is cos 60 degree E1 minus sin 60 degree E2, and E2 prime, the result of C acting on E2 will be minus sin 60 degree E1 minus cosine 60 degree E2, and using this the matrix representation becomes C minus S minus S minus C. The first case where you have to be really careful about this column by column rule rather than the row by row rule is when we meet our first non-symmetric representation matrix. This is the matrix corresponding to the rotation through 120 degrees, D. And of course, when you carry that out, E1 turns to 120 degrees and so does E2. And you can easily write down E1 and E2 in E1 prime and E2 prime in terms of the old E1, E2 using cosine and sine 60 degrees again. And now what you end up with is minus C S. This forms the first column. Going back, let me just show you that E1 became E1 prime, which is minus C E1 plus S E2. So the coefficients minus C and S, they form your first column. And minus S minus C, the coefficients for E2 prime, they form the second column. And this is how you land up with this particular matrix. Finally, the other rotation through 240 degrees, also can be written down in terms of the same numbers C and S, and it's straightforward to see that this is what the matrix representation is going to look like. So now we have 6 matrices, 6 2x2 matrices, which furnish a representation of the group S3. This in fact is the two-dimensional representation of the group S3 that we had seen before. I have just repeated this simply to keep this particular lecture complete within itself. This also happens to be an irreducible representation, one of the irreducible representations the group S3 has. We will now turn to the question of putting these two things together. That is, what happens to the vertices when you carry out a group operation, and what happens to the atomic displacement vector, and then use that to build up the action of the symmetry group on the entire space of molecular vibrations. Let us now put these two actions, the action of the group elements on the vertices of the triangle and the action of the same group elements on the vectors attached to these vertices, together, and use that to create a representation on the space of molecular configurations. Let me just draw a picture that will help us to understand how this goes. On the left, in the red shaded region, you have the original configuration. The red triangle inside is the equilibrium location of all the atoms. The blue triangle depicts the situation when the atoms have been displaced from the equilibrium position. This is of course the same picture that we had used a while ago. And as we have stated, we can describe this particular configuration by attaching basis vectors E1, E2 to the first atom, E3, E4 to the second atom, and E5, E6 to the third atom. We can of course talk about the action of a group element by looking at what happens to the coordinates x1, x2 up to x6 under the action of the group operations, but it is actually more convenient to just ask ourselves what will happen to the basis vectors under the same group operations. The very first thing that we are looking at is the identity operation. Now this of course is very trivial, nothing changes in the identity operation. Anyway, that thing has been shown in blue on the right, and that blue diagram, the diagram with the blue box, shows what happens to the configuration on the left if we apply the identity to it. Of course, nothing happens to the configuration, and in particular, if we focus on the basis vectors, E1 prime is the same as E1, E2 prime is the same as E2, and so on. And this obviously tells us that what we are going to get as a matrix representation is going to be simply the identity matrix, the 6 by 6 identity matrix. Now, I have been saying that this particular representation that we are trying to build up here, of which this is just one example, is essentially obtained by putting together two representations. What happens to the vertices and what happens to the vectors. And in fact, you can easily check to see that this identity matrix is nothing but the direct product of these two matrices. The 3 by 3 matrix, which tells us what happens to the vertices under the identity operation, and the 2 by 2 matrix, which tells you what happens to the vectors, basis vectors, in a two-dimensional representation under the identity operation. Of course, this is way too trivial a statement to make, because the identity, of course, does nothing anyway. But let us now see that this same pattern is going to hold for other non-trivial group elements as well. So let us go on and take a look at what happens to this original configuration of the displaced atoms, which we have drawn on the left here, when you carry out the operation A, which, remember, is a reflection in a vertical median, the median through the top atom straight down. And of course, what happens is straightforward. You can easily imagine what's going to happen, or you can draw the picture yourself and see that what is going to happen ultimately is that the blue shaded triangle is going to flip over in a way. But it's easier to decode what happens in terms of the basis vectors. E1 is going to flip over and become minus E1. E2 is going to stay E2. E3, now this is a bit more complicated, because it is not only true that E3 is going to flip over, that it will, but E3 will actually not flip over and stay at the same place. After all, the vertex which carries the vector E3, the vertex on the left of the figure, actually flips over to the right under the reflection. So E3 prime is actually the vector in blue on the right hand side, and that is what used to be negative of E5, or what is minus E5 in terms of the old basis vectors. E4 does not change in direction under the reflection, but it switches over to the other atom. So E4 becomes E4 prime, which is E6. E5 becomes minus E3, and E6 becomes E4. So putting all these together, we can find out the 6 by 6 matrix representation for the element A. In this case, as you can easily see, that this 6 by 6 matrix can be imagined as being broken up into a lot of 2 by 2 blocks. You can see a minus 1, 0, 0, 1 block on the top corner, another minus 1, 0, 0, 1 block somewhere near the bottom of the middle, and another one near the middle of the last column, minus 1, 0, 0, 1, the same thing. And this really is a result of the direct product nature of this representation that we have been talking about. In fact, this particular matrix representation is nothing but a direct product of the two matrices 1, 0, 0, 0, 0, 1, 0, 1, 0, which talks about what happens to the vertices under the operation A. 1, 0, 0 in the first column simply means A stays A. 0, 0, 1 in the second column means B becomes C, and 0, 1, 0 in the third column means C becomes B. So the first matrix here is simply the matrix which tells us about the action of the group element on the vertices. This is being producted with, or you are taking a direct product of this with the matrix minus 1, 0, 0, 1. So each of the ones on the left hand side gets replaced by minus 1, 0, 0, 1. Each of the zeros gets replaced by 0 times minus 1, 0, 0, 1, which is of course 0, 0, 0, 0. So that actually is the structure that you can see in the original matrix. So this of course bears out in this example that you do have a direct product representation here, direct product of the representation which tells you about what happens to the vertices and the representation that tells you what happens to the vectors. Continuing on to even more non-trivial cases, the reflection B, well, under reflection B, E3, E4 combines two combinations of E3, E4. It becomes cosine 60 degrees E3 plus sine 60 degrees E4 and sine 60 degrees E3 minus cosine 60 degrees E4. That should not come as a surprise. After all, this is exactly how the two basis vectors that we had in our two-dimensional representation transformed under the action of B. The pair E1, E2 transforms in a way which is very similar, but instead of becoming a mixture of E1 and E2, it becomes a mixture of E5 and E6, simply because under this reflection B, the top atom actually comes down to the right hand corner. So E1, E2 has now moved to a location which actually is expressed in terms of E5 and E6. And a very similar thing has happened for E5, E6 as well. Can immediately write down the matrix representation for this. And if you do that, you can once again clearly see the block structure which indicates that you actually have a direct product representation. In fact, the direct product I can even read off directly from here. I can see three blocks in the first pair of columns. The top 0, 0, 0, 0 just says that there is a 0 in the original matrix on the left. Then you have another 0. Then you have 1. 0, 0, 1, 0, 1, 0, 1, 0, 0. That is being direct producted with the matrix CS minus C. And that is exactly what is being written down here. So once again, this action is really the direct product of just what happens to the vertices with just what happens to the vectors. And this pattern repeats throughout. I will not go on and explain each and every step to you because you should be able to work out all these steps. Now that we have the 6-dimensional representation matrices, which tell you how the group acts on molecular vibration configurations, let us consider the character of this representation. The character, of course, is all important because it will help tell us about the reduction of this particular representation. It will tell us which Arabs go in making up this representation. Now, the character, of course, maps every group element to the trace of the corresponding matrix. And the trace, of course, is simply a total contribution of how much of each basis vector retains itself under the operation. That is, you just look at the diagonal element, which is after you apply the operation, how much of E1 is still in E1, how much of E2 is still in E2, and so on. Now, it is very easy to see that for D and F, the rotations, each and every basis vector moves to the basis vector for a different atom. So, it's impossible for any one of them to contribute anything to the original piece. That is, they will not have any diagonal contribution whatsoever. Can clearly see this from the matrix representation of F, for example, which clearly has zeros right down the diagonal and hence a trace of 0. But the direct product version that you saw a while ago also clearly tells you that the zeros down the diagonal of the matrix on the left simply tells you that none of the atoms stay in their own locations when you do this rotation F, and as a result, all the diagonal elements of the direct product matrix must be 0. You don't really need to take a look at the matrices for this. All you need to realize is that when you rotate things around, every atom changes, so the basis vectors just switch on to other atoms and hence cannot contribute to the original value at all. Now, for identity, the character is very simple because for the identity, of course, the matrix is the identity matrix, and in every representation, the character of the identity is simply the dimensionality of that representation. So, in this case, it's 6. What about the character of A, B, and C? Well, for A, B and C, there is one atom exactly which does not shift, and that is the only atom which will contribute to the trace. However, if you look at the reflection matrix, that is what happens to the vector which is attached to that particular vertex, that always ends up having a zero trace. And this is a simple consequence of the fact that if you do a reflection in 2 dimensions, you have exactly 2 eigenvalues, one for a vector which is along the line of reflection, so does not change, and -1 for a vector which is perpendicular to the line of reflection and hence flips over. So because the 2 eigenvalues are 1 and -1, the trace is always 0, the sum of the eigenvalues, and hence even the one atom which could have contributed because it did not move around actually contributes nothing. So we end up with this final result that for D and F and A, B and C, the character is 0, whereas the only element which a non-zero character in this particular case is the identity, and that has a character of 6. So this is what the character table looks like. Let me quickly remind you that the C1, C2, C3 that you see at the heading of the columns here are just the 3 classes. C1, the identity alone, C2, the 3 reflections, and C3, the 2 rotations, 2 non-trivial rotations. And the 1, 3 and 2 that you see on the top left are simply the number of elements in each class. And the character table for this particular representation has, of course, only one row because we are talking of only one representation, and that row has elements 6, 0 and 0. You may have guessed that the calculation of the character for this particular representation could have been simplified by the fact that this is a direct product representation of 2 different representations. And you would be right. This is one of the results of group representation theory that we haven't covered yet, but it is an important enough result so that I need to bring it out to you at this stage. We already have our result. We have found the characters for each and every element in this particular representation, but as I said, the result for characters of a direct product representation is important enough that we should devote some time to it and use that result to rediscover this one. So for a direct product representation matrix, you know that what you have to use are double indices ij and kl, pairs of indices, one referring to each representation, and dA cross B of G, the ijklth element of that is actually a product of the ikth element of DAG and jlth element of DBG. So from here it follows trivially that the trace of the direct product representation matrix on the left is what you would obtain if you were to put K and L equal to I and J respectively, hence getting a diagonal element, and then summing up over I and J. So this is what the character is. But if you now replace dA times B, ij comma ij, by its corresponding result in terms of the individual matrices, you get DAG II and DBG JJ, summed over I and J. Obviously, in this case, the two sums can be done independently. Only the first matrix has I index on it. The second matrix has only the J index. And if you just do the sums independently, you definitely get trace in the representation A of G, and from the second sum you get trace in the representation B of G. So this simply turns out to be chi AG times chi BG. So this is the simple result that we have. For a direct product representation, you can find out the character of every group element just by multiplying the characters that you had in the individual original representations. Now here, in this particular example, we have two representations in place. For us, let us call them chi A and chi B respectively. These are the characters that we are writing down. The characters for chi A are simple. Under C1, the identity, none of the elements move. So you have ones right down the diagonal, and as a result, what you are going to get is a 3 on this particular entry, and that's obvious because we have a three-dimensional representation. On the second class of reflections, precisely one atom does not move. All other atoms, there are two other atoms, switch. And so you are going to get a character of 1. And under rotations, that's the third class, the non-trivial rotations, you are going to get a trace of 0 simply because all the atoms switch position. So you get 3, 1, 0. For chi b, on the other hand, the result is 2, 0 and minus 1. This is again something which is very well known. We have already seen this before. In fact, this is the two-dimensional irrep for this group S3, and we already know the character for that. You could just, of course, as easily figure out these characters just by looking at the representation matrices that we had worked out a while ago. Now, this immediately tells us that the direct product representation, the representation that we are using for molecular vibrations, simply has characters which are 3 times 2, 1 times 0 and 0 times minus 1, hence 6, 0, 0. So obviously we are getting back the result that we had obtained earlier. There is just another way of finding that result, and since direct product representations are actually very, very common, it is important to find out characters for direct product representations, especially if you are asking how do these direct product representations reduce. And there, this particular formula that you can get the characters for the direct product representations just by multiplying the characters for the individual representations turns out to be a very useful formula to have handy. Now, from the characters that we have worked out of our symmetry group's action on the space of molecular vibrations, it is obvious that this particular representation is a reducible one. In fact, we knew that already because we have already seen before that S3 has only 3 irreducible representations of dimensionality 1, 1 and 2 respectively, and thus a 6-dimensional representation has to be reducible. So what exactly is the reduction here? This is of great importance because, as we will see, this contains all the information about the degeneracies of normal frequencies and so on. We can carry out the reduction using the standard character table for S3 that we had already worked out before. Just to remind you, in the character table of S3, you will have 3 rows for the irreps. We are labeling the irreps A1, A2 and curly E, which is sort of a standard labeling. Chi A1 stands for the identity or trivial representation in which every element is mapped to the number 1. Chi A2 is called the pseudoscalar representation, here including the identity. The rotations are all represented by the number 1 and the reflections are represented by the number minus 1. Why this is called a pseudoscalar representation should be pretty clear to all of you because this is exactly how a pseudoscalar behaves. Stays the same under rotations and changes sign under reflections. The two-dimensional representation that is furnished by, say, vectors in a plane simply has the characters of 2, 0 and minus 1. Let us add our own representation as a last row here. That of course has characters 6, 0, 0. Now we can actually figure out the reduction of this particular representation without doing any calculations, for the simple reason that we already are aware of another representation which has exactly the same character, namely the identity class has exactly the same character as the number of elements in the group, and all other classes give you 0 for characters. And that one is the regular representation. This representation is not the regular representation, but it has the same characters as a regular representation, which actually means that it is equivalent to the regular representation. You can find a similarity transformation which will transform our 6x6 matrices to the 6x6 matrices that we found for the regular representation. But more importantly, since the reduction or the number of times a given irrep occurs in a particular representation depends only on the characters, this should have exactly the same reduction as a regular representation. And we know that the regular representation contains each and every arep as many times as the dimensionality. That is, A1 and A2 will occur once, and E, being a two-dimensional representation, will occur twice. And that brings up this entire 6 dimensions that we want here. You can of course calculate the same result simply by using the standard formula for calculating M alpha, the number of times a particular arep occurs in a representation. And I'm just showing you one such calculation. You have to divide this product by the number of elements in the group, that is why you have a 1 by 6 in the front. The 1 times 1 times 6 is simply something which comes from multiplying the number of elements in the class by the character of the representation A1 and the character of your representation. The second term, 3 times 1 times 0, again number of elements in the class C2 times the character for class C2 in our representation A1 and the character for class C2 in the representation that we are using, plus 2 times 1 times 0 coming from a similar source, and all this will together give you M1 of 1. Very quickly we can figure out that M2, the number of times A2 occurs in this, will also work out to be 1, and M3 will work out to be 2. As I said, we already knew this because this particular representation has the same characters as a regular representation. So our representation D is actually a direct sum of 1 copy of A1, 1 copy of A2 and 2 copies of E. Now, as I said earlier, there are actually zero frequency modes which are also taken into account here. There are 2 translational modes and 1 rotational mode. The 2 translational modes transform obviously like DE, the 2-dimensional representation that we have, simply because the 2 translations along X and along Y transform under the group operation exactly the same way as our basis vectors E1, E2 of R2 did. So, 1 copy of DE accounts for the translations. It so happens that rotations actually transform under DA2. This is again not so difficult to understand. We are going to explicitly show this in the next lecture. But rotations, after all, involve angular momentum, which is a pseudo vector, and that is actually seen in the -1 that you have under reflections. If you take these modes away, what you get are the vibrational modes, and the vibrational modes turn out to be just one single irrep A1, and the transformation and the way that, and so the representation which tells you how that and so the representation which tells you how the representation that tells you how the vibrational modes transform under the action of the group elements is a direct sum of a single copy of A1, the identity transformation, and another copy of this 2-dimensional representation DE. So what does this mean for us physically? We will explore this question in great detail in the next lecture, which is essentially part 2 of this lecture. But let me quickly point out one thing. The fact that there is a 1-dimensional irrep in this decomposition, and moreover, the fact that this 1-dimensional irrep happens to be the identity representation, tells us that there is a normal mode which is invariant under each and every one of these group operations. So the way in which the molecule vibrates must be such that whether you reflect along A, B or C, or you rotate through 120 or 240 degrees, the transformed mode would look exactly the same as the original one. This should be a good enough hint for you to figure out exactly what kind of oscillations occur here. The fact that there is a 2-dimensional irrep actually tells us that the 2 of the frequencies of vibration are actually going to be equal to each other. So you have a degeneracy here. We will explain in more detail how this particular information can be obtained, and there of course we are going to use the Wigner-Eckart theorem as an important tool. All that will be in the next lecture. We will also talk about how to find the normal modes by applying the projection operators that we had talked about in the last lecture. And we will also try to look at an explicit model where we can figure out what the frequencies of oscillations are by using these techniques which we have learned from group theory. So long. Okay, all that is, of course, for the next lecture. Until then, bye.